So today's really just going to be a super short lesson on something called the squeeze theorem. So the squeeze theorem is something we use in calculus when we're trying to evaluate a limit of a function that we know to be between two other functions. So what I mean is, if we have our axis like this, so let's say we have some function in green here, we'll call it f of x. Okay, and then we have another function, say in blue, we'll call it, say it's going down here, we'll call it g of x. So this is g of x. So let's keep the theme here. Let's go with h. So h of x, if we know that h of x near some point a, so we'll call this point a right here, if we know it's between f of x and g of x, so if we know at some point near a, the function's between f of x and g of x, we can write this here. So we can say, if we know that g of x, say it's in the middle here, right, the limit of f of x is going to be higher because it has a greater y value. Right, so if that's less than the limit, or sorry, that's less than f of x, or g of x is in, I did the wrong color here. So g of x is the one on the bottom, so if this is h of x, right, if h of x is between g of x and f of x like this, and then I did g of x like this, there we go. So if we know this to be true, if we know that h of x, some function, is between the two other functions, g of x and h of x, we can also deduce that the limit as x approaches some value a for g of x is going to be less than the limit as x approaches a for h of x, which is going to be less than the limit as x approaches a of f of x. Okay, so this might seem obvious to you. You might be thinking, well, obviously, if, oopsies here. You might be thinking, well, obviously, if f of x is higher than h of x, which is higher than g of x, we know that their limits approaching some point a, right, some point a over here, is going to be somewhere between f of x's limit and g of x's limit. But this statement right here actually has a lot of practical value. So when we're trying to evaluate limits of something like maybe sine of x over x, it has a lot of useful applications. So let's just see down here. So this first example here, prove using the squeeze theorem that the limit of alpha cubed times sine of 2 over alpha as alpha approaches 0 equals 0. So without the squeeze theorem, this might be a bit daunting. We might be thinking well, how can we visualize this? The graph's going to be looking kind of funky, right? So what we have to start off with is, typically when we're using the squeeze theorem, we're using sine or cosine functions. So you'll see lots of trig functions pop up in squeeze theorem questions. So what we know is that the sine of 2 over alpha, right? 2 over alpha, for any constant, any scalar for alpha, it's just going to be somewhere between -1 and 1. So even though 2 over alpha looks kind of weird, it's not just like sine of x. Alpha's our variable, but no matter what this function looks like it could look like this and then go up and then do all this weird stuff. But we know that for its entire path, it's always going to be between or equal to -1 and +1. Okay, so what we're going to write is -1 is less than or equal to sine of 2 over alpha, which is less than +1. Okay, so if this is sine of 2 over alpha, blah, 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 we know that it's going to be greater than -1, and it's going to be less than +1. So if we know that, right, then we have to think, well, right now it's sine of 2 over alpha. How can we get it to alpha cubed times sine of 2 over alpha? And the cool thing about the squeeze theorem is that we can just multiply this part right here by alpha cubed. And if we do that, we have to multiply it by, alpha cubed by this number and this number. So if we multiply our original function by some other function or some other component, we have to do it to every component. So we're going to have negative 1 times alpha cubed is going to be less than or equal to alpha cubed times sine of 2 over alpha, which is less than or equal to positive 1 times alpha cubed. And this might also make some intuitive sense. So if we know this to be true, well, if we're just adding some scalar multiplier in here, like 5 or 15, if it was true before and we're just adding some, we're just making it a product, it's going to be true. This statement's going to hold true after we add this multiplier in there. Okay, so what we really have now is we can get rid of these negative ones here. We have negative alpha cubed is less than or equal to alpha cubed times sine of 2 over alpha, which is less than 1 times alpha cubed, so just alpha cubed. Okay, and what we can do now is, if this holds true, then we should also be able to take the limit of each thing. So the limit of negative alpha cubed as alpha approaches 0, because remember in the question that's what we're analyzing, is the limit as alpha approaches 0 is going to be less than the limit of alpha cubed times sine of 2 over alpha. Oh, sorry, I didn't write the limit here. So the limit as alpha approaches 0 of alpha cubed times sine of 2 over alpha, right? And we know that that's going to be less than the limit of alpha cubed as alpha approaches 0. So notice how this is the original question. This is what we're actually looking for. But we broke it down into sections where we know what the graph of alpha cubed looks like. It's just like x cubed. So if we have negative alpha cubed, that graph's just going to look like this. It's going to start high, come down, and then go back down again, right? So this is kind of like the flipped version of x cubed. And positive alpha cubed is going to look like this. It's going to be the opposite. So the limit of both of these as alpha approaches 0, we could figure that out just by substituting in 0 for alpha, or just looking at the graph. So as we get closer and closer to this point 0 here at the origin, the limit, the y value, is going to approach 0 as well. So we can just sub in 0 where we see these two limits. So we know that 0 is going to be less than or equal to the limit as alpha approaches 0 of alpha cubed sine 2 over alpha, which is less than 0, because these are both 0. The limits are 0 if we substitute it in. Okay, well, if this is 0, and this is 0, and this is between or equal to the two boundaries, kind of sandwiching it together, is squeezing it together, the only thing that we can deduce is that this side right here, this inside function, is also 0. So the limit as alpha approaches 0 of this is also 0. Okay, so the squeeze theorem allows us to kind of conclude that if this limit to the left of it is 0, which is less than or equal to the main limit we're looking at, and if that limit is less than or equal to 0, so it's kind of being sandwiched, we know that the limit itself is also going to be equal to 0. Okay, let's look at another example here. So determine the limit as x approaches infinity of cosine x plus pi over x using the squeeze theorem. So notice if we were to plug in infinity for x, we would get the cosine of infinity plus pi over infinity. So this is an indeterminate form, because anytime we divide something by infinity, or we have infinity inside of a trig function, there's no way to really analyze that effectively, because infinity isn't a real number. And if we say like cosine of infinity, that doesn't really mean anything, okay? So what we want to do is we want to look at what can we start with and what can we multiply. So cosine of x plus pi over x, that's really the same as cosine of x plus pi times 1 over x. So first of all, before we worry about the times 1 over x, let's just focus on this cosine right here. So what is cosine always between? Even though this is cosine of x plus pi, this is just a horizontal shift. So if we look at the graph of cosine of x plus pi, we know because there's no number in front, there's no a value here, this graph's always going to be between +1 and -1. So cosine, it starts at the top here, goes down, and it kind of oscillates between these two values here. Cosine of x plus pi, it's the same thing, it's just shifted to the left by pi units, so it's going to look like that. It just kind of oscillates forever. Okay, so if this is +1, this is -1, we can write cosine is somewhere between that, no matter what this is. So this could be 1,000,000, this could be 5, this could be -15. The cosine of anything is always between 1 and -1 if it's a real number. Okay, so now let's kind of use the squeeze theorem here. We have the cosine of x plus pi, but we want to take the limit, first of all, as x approaches infinity, and we want to add this over x. Okay, so let's look what we did up here. So first we had the sine function, right? And then we added this multiplier in, this alpha cube. So let's do that. Let's multiply it by what it really is. It's not just cosine of x plus pi, it's cosine of x plus pi times 1 over x. So we're going to take this -1 and we're going to multiply it by 1 over x, which is really just dividing by x. Okay, and then we're going to add our 1 over x here, so it's going to be cosine of x plus pi over x, which is what we had, and that is less than or equal to 1 over x. Okay, so before we take the limits, let's just look at what's going on here. 1 over x, okay, 1 over x looks something like this. I'll draw that a bit better here. So 1 over x is going to look something like that. And then it's going to kind of repeat in this third quadrant here. Okay, and then -1 over x, that's just going to be the opposite. It's just the negative version, so it's flipped in the x-axis. Okay, and notice how we're looking for the limit as x approaches infinity. So notice how if this is our x-axis, if we're looking for how these functions behave as x approaches infinity, that's moving this direction to the right. So see how in these graphs, as x approaches infinity for both of them, they both get closer and closer to 0. So if we were to kind of go on forever, the top and bottom side, they would both flatten out. They'd never reach 0, but they get closer and closer and closer until it was infinitesimally close. Okay, so what we're really saying is we're squeezing this inside function between the two, and we're saying, well, if the limit as -1 over x approaches infinity is 0, and the limit as +1 over x as x approaches infinity equals 0, and this function is between them, so if this function, whatever it looks like, it could be some squiggly weird line, if it's between them, its limit as x approaches infinity also has to be 0. So the answer for this is going to be 0, but let's just finish it out and write the limits like we did in the last one. So we're going to take the limit of everything. We're going to take the limit of -1 over x as x approaches infinity, right? Because that's what the question's asking, is less than or equal to the limit as x approaches infinity of cosine x plus pi over x. And we know that's going to be less than the limit as x approaches infinity of +1 over x. So I just drew it out, but let's just substitute an x. So this is really going to be -1 over infinity is less than or equal to the limit as x approaches infinity of cosine x plus pi over x, and that's going to be less than 1 over positive infinity. So both of these limits are 0. So anything over infinity, if it's a constant, is just 0. And same with this positive one here. Positive 0 and negative 0 is not going to make a difference. So this function, its limit is going to be between or equal to 0 and 0. And I drew that out, right? As we got further and further away, so if we drew our x-axis here, if we had our two functions like this, whoops, if the function that we're talking about, this limit, is between the two, whatever it looks like as x gets really, really big, it's going to flatten out, and the limit will be equal to 0. Okay, so that's what the squeeze theorem is. Not a ton more to talk about that, just a couple neat applications. Like if you weren't sure how to solve this before with our regular limit techniques or L'Hopital's rule or whatever it was, now we can solve it with the squeeze theorem, which is kind of cool. So I hope this is helpful. Drop a comment if you have any questions. I'll be sure to answer them, and I'll see you in the next video.